Gazing upwards at the infinite beauty of the universe, it's easy to miss the marvels flitting silently overhead. Even at this very moment, a fleet of human ingenuity streaks across the black canvas. Satellites, space probes, and the International Space Station, all diligently working to improve our lives here on Earth. But their incredible journeys wouldn't be possible without the mighty thrust of rockets, those fiery engines that propel them skyward and guide them on their missions. Building a rocket involves a complex dance of design, engineering, and meticulous construction. It all starts with a concept: what the rocket will be used for, how much it needs to carry, and where it's going. Engineers translate this into detailed blueprints, choosing materials and calculating the forces involved. Rockets are built tough, using high-strength metals like aluminum, titanium, and steel. A rocket's journey to the cosmos hinges on a delicate balance. Its body, crafted from incredibly thin sheets, a mere 17 millimeters thick, needs to be both lightweight and remarkably strong. To achieve this, engineers employ a special cutting technique, transforming the sheets into an intricate iso grid structure. This ingenious design, at roughly 2 millimeters thick, sheds weight while simultaneously boosting the structure's resilience. Finally, these shaped pieces are meticulously combined to form a cylinder, the heart of the rocket, its fuel tank. The rocket resembles a giant, sharpened pencil, its slender form dominated by fuel tanks. These tanks store two separate types of fuel: liquid hydrogen and liquid oxygen. Keeping them apart is crucial for the incredible speeds this rocket can achieve. With two powerful engines and each stage boasting dedicated tanks for each fuel type, the design prioritizes efficiency. But the most critical difference lies at the core, within the heart of the rocket engine itself. Inside a powerful chamber known as the combustor, hydrogen and oxygen are united with ferocious intensity. This tempestuous fusion ignites a colossal firestorm, churning out high-pressure gas that rips through the engine at speeds exceeding the crack of sound. This phenomenal process unleashes unimaginable heat, reaching a blistering 3,500 degrees Celsius. Imagine the incredible strength required by the engine to endure such punishing temperatures. The journey begins with the very building blocks of the rocket. Each part, from the colossal body to the intricate engines and voluminous fuel tanks, is meticulously crafted. Skilled workers wield the tools of their trade, machines that cut and shape with incredible precision, welds that fuse metal into unyielding strength, and even the marvels of 3D printing, where components literally take shape layer by layer. Through these techniques, the disparate pieces slowly coalesce, forming the magnificent machine that will one day pierce the veil of our atmosphere. Once meticulously assembled, the entire rocket is then carefully transported to its launchpad in Tanegashima, a southern island in Japan, poised to unleash its power and propel humanity's dreams skyward. The tension crackled in the air like static electricity. A massive, specially designed vehicle lumbered onto the scene. Its precious cargo, the gleaming rocket, poised for its fiery ascent. This behemoth gently deposited the vessel on the launch pad, a concrete jungle where the final act of meticulous preparation would unfold. Here, the clock would tick down relentlessly, marking the passage of moments until the mighty engines roared to life and the rocket pierced the veil of the atmosphere. With a powerful thrust, the spent first stage engine is jettisoned, falling away. The second stage engine roars to life, propelled by a significantly lighter rocket. In the zero-gravity embrace of space, the second stage accelerates like a cheetah, its speed climbing steadily. Now, we're truly spaceborne. The mission? To deliver a precious satellite to its designated orbit. To achieve this, the rocket needs to reach a mind-boggling 8 kilometers per second, a speed that would allow it to travel the same distance a Japanese bullet train covers in 3 hours, in just 1 minute. Soon, the satellite will be released, its mechanical heart taking over the eternal dance around our planet. Once that's done, our little rocket will have fulfilled its purpose, a testament to human ingenuity. The aircraft engine manufacturing process is extremely complicated. Here's a breakdown of why. Advanced materials. They are built using high-strength, lightweight materials that can withstand extreme temperatures and pressures at high altitudes. These specialty alloys require special handling and processing techniques. Tight tolerances. Every part needs to be manufactured to incredibly precise specifications to ensure efficient operation and safety. Even tiny imperfections can disrupt airflow or cause catastrophic failure. Multiple manufacturing techniques. A wide range of methods are used to create the various engine components. These include casting, forging, grinding, machining, and even specialized techniques like electron beam welding. Assembly complexity. The engine is a complex machine with numerous parts that need to fit together perfectly. Each engine can take years to assemble after the design and testing phase is complete. The jet engines that operate in modern passenger aircrafts are built of many complex structural assemblies whose manufacturing methods vary to reduce their production costs and weight, which in turn reduces the operating costs of jet engines. The precision casting technology that has been applied so far is often replaced by implementations of complex thin wall assemblies. Aircraft engines endure tremendous stress, so exotic alloys like nickel titanium are used. These are formed into various shapes through processes like forging, shaping metal with compressive force, and casting, pouring molten metal into molds. These designs are manufactured with advanced methods of joining materials, followed by precision machining of the assemblies. The numerous machined parts are meticulously assembled into subsections like the compressor, drawing in air, combustor, burning fuel-air mixture, and turbine, extracting energy from hot gases. You can see in the video the process of assembling the Trent XWB engine. The Rolls-Royce Trent XWB is a high-bypass turbofan produced by Rolls-Royce Holdings. In July 2006, the Trent XWB was selected to power exclusively the Airbus A350. The Trent XWB is an axial flow, high-bypass turbofan keeping the characteristic coaxial three-shaft architecture of the Rolls-Royce Trent. The 3.00 meters, 118-inch fan is driven by a 6-stage turbine. An 8-stage IP compressor is powered by a 2-stage turbine, and a 6-stage HP compressor is turned by a single-stage turbine, rotating in the opposite direction of the two others. The annular combustor has 20 off-fuel spray nozzles, and the engine is controlled by a dual-channel FATIC. The Trent XWB features a 2-stage IP turbine rather than a single stage from previous Trent engines. The 97,000 lbf 430 kN engine version for the A350-1000 maintains the same 3.0 meters fan size and a 5% larger core. The additional thrust will require the fan to run 6% faster, which will require strengthening to withstand the increased fan blade forces produced. It has thicker titanium fan blades and a stronger fan casing, and takes advantage of technologies developed through the European Environmentally Friendly Engine Research Program. Its core operating temperature capability will be increased. highly efficient. The Trent XWB delivers 25% lower fuel burn and CO2 emissions compared to previous generation engines. This translates to significant cost savings for airlines and a reduced environmental impact. Versatile range. The engine has the power to fly long routes, currently powering the world's longest commercial flights. Quiet operation. The Trent XWB is designed to be one of the quietest engines in its class, contributing to a more pleasant experience for passengers and those living near airports. Popular engine. With its efficiency and performance, the Trent XWB has become the fastest-selling wide-body engine ever, with over 1,800 engines in service or on order. On December 15, 2023, Turkish Airlines became the largest operator of Trent XWB engines after ordering an additional 140 engines. Overall, the Rolls-Royce Trent XWB is a powerful, efficient, and versatile engine that has helped to make the Airbus A350 a popular choice for airlines around the world. Jet engines are marvels of modern engineering, and their complexity is a major reason why. They are essentially giant air compressors that use the compressed air to burn fuel and create thrust. This seemingly simple process requires a symphony of thousands of precisely machined parts working together at incredible speeds and under extreme temperatures. Number of parts. A modern jet engine can have anywhere from 30,000 to 50,000 individual parts. Each of these parts needs to be manufactured to exacting tolerances to ensure proper function and safety. Material science. Jet engines operate in a harsh environment. The temperatures inside the combustion chamber can reach over 2,500 degrees Celsius, 4,532 degrees Fahrenheit, and the turbine blades spin at thousands of revolutions per minute. The materials used in jet engines need to be able to withstand these extreme conditions without failing. Tight tolerances. The parts in a jet engine need to fit together perfectly. Even tiny gaps or misalignments can cause major problems, such as reduced efficiency or even engine failure. Manufacturing processes. The manufacturing processes used to create jet engine parts are complex and often require specialized equipment and highly skilled workers. Integration and testing. Once all the parts are manufactured, they need to be assembled and tested to ensure that the engine works properly. This process can be very time-consuming and expensive. The complexity of jet engine manufacturing is a major challenge for the aerospace industry. However, it is also a testament to the ingenuity of engineers and the skill of manufacturing workers. The production timeline for aircraft jet engines can be broken down into two main phases: development and testing. This initial phase can take anywhere from 2 to 7 years, depending on the complexity of the engine design. This involves extensive research, design, engineering, and rigorous testing to ensure the engine meets performance and safety standards. Manufacturing and assembly. Once the design is finalized and tested, physically building the engine takes about 2 years. This involves constructing numerous intricate components, assembling them with high precision, and conducting final inspections. So, the total time for a brand new jet engine design to be ready for commercial use can range from 4 to 9 years or even longer. There's a focus on quality and safety throughout the process, so expediting this timeline isn't usually prioritized. A single jet engine can cost $16 million, and on a transatlantic flight will consume 36,000 gallons of fuel, which at today's airline fuel prices comes to around $54,000 per trip, or more than $5,000 an hour. Maintaining the aircraft on the ground can add hundreds of dollars per hour. Although fuel costs have been falling, airlines are still pursuing ways to reduce running expenses. Some areas being pursued include increasing fuel efficiency of jet engines, optimizing flight paths, and improving maintenance. With tens of thousands of individual parts and their enormous complexity, airlines will not be able to control the status of all parts. It is imperative to have a maintenance plan and major overhauls to keep the engine in top condition. Imagine a checkup at the doctor's. Jet engines go through similar routine checks to catch minor issues before they snowball. This might involve visual inspections, oil changes, and filter replacements. Jet engines are incredibly complex machines operating under extreme conditions. The high temperatures, constant vibrations, and friction from moving parts can cause wear and tear. Left unchecked, this wear could lead to sudden engine failure, which could be catastrophic during flight. Regular maintenance helps identify and address these issues before they become serious, ensuring the engine runs smoothly and safely. Like any machine, jet engines lose efficiency as parts wear down. Regular maintenance helps keep the engine in top condition, optimizing fuel consumption and overall engine performance. This translates to lower operating costs for airlines and smoother operation for passengers. In essence, jet engine maintenance is all about preventing problems and keeping the engine running safely and efficiently. Think of it like regularly servicing your car. It might seem inconvenient, but it's crucial for safe and reliable transportation.